Hello, my name's Toby Walsh, and I must begin by apologising for not being there in person. I'm actually on the plane flying to Montreal as we speak. Unfortunately, I couldn't get there any sooner, but I therefore look forwards to seeing many of you during the next week in person. I want to talk about some new work where I've been looking at approximate mechanism design for the facility location problem, where we're exploiting predictions to improve the quality of the answers. So the setting is one of the simplest problems in social choice, facility location. And we're looking at a particular simple setting of facility location where we're locating facilities along the real line. So it's the one-dimensional facility location, and we're worrying about how to allocate the facility along the real line to fairly serve the agents. We're thinking about the egalitarian flavor of the problem, where we're interested in minimizing the maximum distance any agent travels. Now, of course, the optimal solution here is just to locate the facility at the midpoint. But unfortunately, that's not strategy proof. And indeed, previous results show that you can't approximate the maximum distance, the minimum maximum distance, better than a two approximation with a deterministic strategy proof mechanism. So a natural reaction when you discover that something can't be returned is to think about, well, how well can we approximate it? How suboptimal can strategy proof mechanisms be? And we're going to add an extra twist to this, which is we're going to assume that we have some predictions as to what the optimal solution is. But suppose we've got some past historical data on where agents tend to be. Can we use that to improve the quality of the outcomes that we return? And we're going to measure the quality in two ways. We're going to look at the robustness, which is what approximation ratio of the optimal objective do we get even when the prediction is incorrect? So, how bad could it be if it turns out our prediction was not a good one? And then consistency, which is how well can we do? How much better can we do when the prediction is actually correct? And so that's the approximation ratio when the prediction is correct. We want the consistency to be as close to one as possible and the robustness to be not too large. There's been some previous work by Agrawal et al. In 2022 looking at approximate mechanism design for the facility location with predictions. And there they propose this mechanism, the min-max-p mechanism, which takes account of predictions. If the prediction is between the leftmost and rightmost agent, it locates the facility at the prediction. Otherwise, the prediction is not, the agents do not straddle the prediction. So we locate the facility at the nearest agent to the prediction. So that would be the leftmost or rightmost as appropriate agent that is closest to where the prediction was. Now, Agrawal et al. Have proven that this is one consistent. So when the prediction is correct, it returns the correct answer, and two robust with respect to optimizing the maximum distance. So when the prediction is incorrect, the worst it can be is that we get a two approximation of the minimal maximum distance. Now, from previous work, it was known that no strategy proof mechanism can be better than two robust. So that might seem to be all that you could usefully say about about facility location mechanism design with predictions in this setting. You can't obviously do better than one consistency, and there's two robustness is optimal. Turns out, though, if you look close at the problem, that you can do somewhat better. And indeed, what we're going to look at is not optimizing the maximum distance, but optimizing the minimum utility. Utility and distance might seem to be close proxies of each other, but it turns out that when we're thinking of approximation ratios, it's actually quite important. There's quite an important distinction between the two. So we're assuming that the agents are on some fixed interval, here 0, 1, but it could be any interval as we can normalize by that, the length of that interval. And then we could define the utility as 1 minus the distance that agents need to travel. Now, when we look at this objective, which is optimizing the minimum utility, min-max p is one consistent again, um, but now it has unbounded robustness. It fails to approximate well problem instances where the distance is large and the utilities are small. So these are the hard problems which are somewhat inequitable, where some of the agents have to travel much further than the others. So instead, we propose a new mechanism which does a better job, has bounded robustness and consistency. This is the truncated minimax B mechanism, where we first take the prediction, we truncate it to the interval A1 minus A, where A is some parameter between 0 and a half, and then we apply min-max P to this truncated prediction and the agent's locations. This gives us a consistency, 2 minus A over 2 minus 2A consistency, and 1 plus A over 2A robustness. And in this graph, I've plotted consistency as robustness. You can see we can smoothly trade consistency between 1 and 1.5 against robustness, which goes, again, unbounded down to 4/3. We've also given a characterization result. You might wonder, well, why are we focusing so much on min-max P and truncated variants of min-max P? Well, it turns out for good reason. We can prove that the only deterministic strategy-proof, anonymous, and Pareto-optimal mechanism that does better than 2 consistency with respect to the maximum distance when we look at predictions aren't the endpoints is min-max P, which is even better. It's 1 consistent, as we said. And min-max P is also the only such mechanism, deterministic strategy proof, anonymous and Pareto efficient, that is 1 consistent with respect to minimum utility. So there's a good reason why min-max P is the focus of our attention. We look at other instances. We look at not just deterministic, but randomized mechanisms. Now, when you're optimizing the maximum distance, the LRM, left, right, middle, mechanism is a natural one to look at. It has optimal approximation ratio of the maximum distance. This picks the midpoint with probability half, the leftmost agent with the probability a quarter, and then the rightmost agent with the remaining probability of quarter. It turns out that that's not so good at optimizing the minimum utility. What is good at optimizing, what in fact has the optimal approximation ratio for the minimum utility is the truncated version of that, LRMT, where we first truncate the agent's locations to the interval 1/3, 2/3, and then apply LRM to those truncated locations. Those 2 mechanisms, LRM and LRMT, don't take advantage of the prediction. So we propose instead a mechanism that does combine LRMT with something that takes account of the prediction. So we sort of hybridize between LRMT and min-max P. So with probability 2A, we call LRMT, and with the remaining probability 1 minus 2A, we call min-max P. So that's taking now account of the prediction with some probability. That turns out to have 2 over 2 minus A consistency and 2 over 3A robustness. And I plotted this on this graph here, and you can see that it's sometimes better than min-max P, and is sometimes worse. I mean, there's not much in it, but it can give better consistency and better robustness, as you see to the bottom right, and slightly worse consistency and robustness in the top left of this diagram. Now, I don't have time to go into all the results you can find in the paper. We also look at 2 facilities. We look at deterministic mechanisms for 2 facilities. We look at randomized mechanisms for 2 facilities. You can see some of these results, a large catalog of results that are described in this table. It turns out, despite the previous work which suggested that min-max P was the only thing, it turns out there's actually quite a rich space of approximate strategy-proof mechanisms that can take account of predictions and use those to improve the quality of answers. It turned out that looking at utility, not distances, was important. It lets us focus on the challenging instances where some agents are necessarily far from the facility and utilities are small and distances are large. And as we found out in the other work I'm presenting at this workshop, that truncating extreme outcomes is often quite helpful for improving the quality of the answers that we return. And we saw that in a number of settings here in approximate mechanism design with predictions. Thank you.